Hi everyone, today we are going to understand Maclaurin series. In calculus, we have understood the rate of change, average rate of change, instantaneous rate of change. We know that suppose we have a curve, any curve, fx be any curve, and instantaneous and average rate of change. Average rate of change is the gradient of the line joining the 2 points, let's say A and B. However, the gradient of the line joining 2 points A and B, instantaneous rate of change is the gradient of the tangent at a particular point. Gradient of the tangent at a particular point. So at an instant, that is tangent. Now suppose you're climbing a mountain from bottom to the top of the mountain. Think of, is there any point or is there more than one point where the instantaneous rate of change or the average rate of change are same? The answer is yes. We'll see in the coming discussion. Now, Maclaurin series is used to approximate, basically to approximate. Approximate what? Approximate complex functions, limits to functions, solutions to differential equations, to definite integration, and so many applications. But Maclaurin series is the extension of Taylor series. What is Taylor series? Let's understand what is Taylor series. Let us say fx be any continuous, which can be differentiated infinitely, the Taylor series expansion at x is equal to a, or centered at x is equal to a, is given by fx is equal to value of the function at a plus first derivative at a divided by 1 factorial to x, double derivative at a 2 factorial x squared plus triple derivative at a divided by 3 factorial x cubed, and so on. And this can be further summed up. It's difficult to write all the terms, so we can write it like this: sigma I is equal to 0 to infinity ith derivative at a divided by I factorial into x minus a whole raised to power I. Now note, what is Maclaurin series? Now if a is considered to be 0, then the Taylor series becomes Maclaurin series. So we can write fx, the derivative value of the function at 0, first derivative at 0, 1 factorial times x plus double derivative at 0 by 2 factorial times x square, triple derivative at 0 divided by 3 factorial x cube, and so on. We can summarize it with the help of sigma in order to make the workings easier. I is equal to 0 to infinity ith derivative at 0 instead of a, ith factorial into x raised to power I, and that is called Maclaurin series. Maclaurin series. Maclaurin series. Maclaurin series. And in IBDP, Mathematics Approaches and Analysis HL, only Maclaurin series questions will be asked. Taylor series as it is not there. Only the Maclaurin series centered at a equal to 0 is there in their syllabus. If for first n terms, this expansion is for infinite many terms. If for first n terms, Maclaurin series expansion can be written as m subscript n x is equal to sigma I is equal to 0 to n, same ith derivative at 0 divided by I factorial x raised to power I. Now if we let n is what? What is n? N is the order of the polynomial. Order of polynomial. Or we can say number of terms. When we expand further, we'll understand. So if we let n approach to infinity, the limiting value of the Maclaurin polynomial as n approaches to infinity will not be nothing but the function which we are approximating. More the number of terms, more accurate will be the approximations. We'll see this with the help of an example. And Maclaurin series converges for any x. So Maclaurin series converges for any x. For any x, and that interval is called the interval of convergence. That interval of values of x for which it converges is called interval of convergence. Or convergence interval. Let's see with the example. Consider simple example. Find the Maclaurin series representation. Find the Maclaurin series representation for, okay, let's just simply write the function. Find the Maclaurin series representation for fx is equal to e raised to power x using derivatives. A part. B part, comment on the value of e. Comment on value of e, which e is approximately given 2.72 rounded to 3 significant figures. We'll find and see what is the comment. Now we have the function which is differentiable infinitely, which is continuous, and the value of the function at 0 is 1. Simplest example, e raised to power x, first derivative, double derivative, e raised to power x for any curve which is continuous and which can be differentiated infinitely, third derivative, and so on. Now Maclaurin series expansion e raised to power x is, first we write the function value at 0, first derivative, we write the formula or the rule as it is, 1 factorial into x, double derivative x squared plus third derivative as it is rule in the previous part, 3 factorial x cube, and so on. Now we substitute the values, 1 plus 1 into x plus 1 into x squared by 2 factorial plus 1 into x cube by 3 factorial, 1 into x4 by 4 factorial, and so on. So that simplifies to x plus 1 plus x plus x squared by 2 factorial plus x cube by 3 factorial plus x4 by 4 factorial, and which is answer to part A. Let's look at answer to part B. Now for n terms, we know for n terms the Maclaurin polynomial for n terms, first n terms, Maclaurin polynomial is given by sigma I is equal to 0 to n ith derivative at 0 divided by I factorial into x raised to power I. Now if we consider the first three terms, or maybe first two terms, let us say first two terms, m2 at, okay, let's say at 1, that will be equal to 1 plus 1, that will be equal to 2, exactly 2. If we consider Maclaurin polynomial of order 3 at 1, that will be equal to the sum of first three values when x is equal to 1. So 1 plus 1 plus 1 by 2, that is 2.5. Maclaurin polynomial of order 4 at 1, 1 plus 1 plus 1 by 2, 3 factorial is 1 by 6, and that is equal to 2.66666 and so on. And Maclaurin polynomial of order 5 at 1, 1 plus 1 plus 1 by 2 plus 1 by 6 plus, okay, so that is 1 by 24, which is equal to 2.70833 and so on. And you can see Maclaurin polynomial of order 5 is approximately equal to 2.71, rounded to 3 significant figures. And if we see further, if we increase, we'll get further accuracy, more closer value. If we see, so more the number of terms, or more higher the order of the Maclaurin polynomial, more accurate will be the, so more accurate will be E is approximately equal to 2.71. So higher the order of the Maclaurin polynomial, higher will be the accuracy of the approximation. Do like, subscribe and share. Thank you.